hello. So this is the last session of the day. I hope it's going to be enjoying. We have our guests over there. You've seen some of them speaking yesterday, particularly Pierre-Emmanuel from Quandela. We had, who am I missing? Constantin. It was the same session yesterday morning. And I think, and me, okay, fine. And the new ones are Tristan Meunier. He had somebody from his team, Oscar Gravier, a couple of days ago. And we have, who am I missing? Pierre Gégère over there from IBM. He's based in France and so on. So the first question I will ask them is, what do you do in life? I mean, what's your job? Maybe I'm going to start with Joseph. He's our guest. I mean, all the other folks are French, so it's not good.
Okay, thank you. Well, I'm Josep Bosch. I'm coming from Qilimanjaro, a startup based in Barcelona. So Qilimanjaro is a full-stack company. We do have a theory team where I'm working more in the operations part, and we also have a hardware team. So we have expertise in gate-based devices, but our focus is on analog computing, based on superconducting qubits. And yeah, why analog? Well, because even though gate-based computing looks very promising, right now there's a problem of noise error correction. And since, as you said in your talk the other day, one of the so probably one of the first applications where we will find advantage will be in quantum simulation. Mm-hmm. And analog devices are very well suited for these kind of applications. So we have decided to with the analog approach, and also in analog you have noise, but because of its nature you are more protected to noise. So you don't need these very costly error correction protocols. My question was, what do you do? So, okay, sorry. I'm on the applications part of Qilimanjaro. We do, in the applications part, we study algorithms. We look at which use cases will be, the quantum computers will give an advantage. Okay. So yeah, we work in different projects with clients, with companies, with research institutes, and yeah. Okay, so next is Pierre-Emmanuel.
Hello everyone, so I'm Pierre-Emmanuel Emerio. I work at Quandela. I'm leading the quantum algorithm team at Quandela, so I'm a theoretician, mostly more computer scientist than a physicist. And I guess, well, of course, I'm working on various projects regarding quantum algorithms, but you also saw yesterday a bit of what we do at Quandela, especially with Ariane over there, about the energetic of photonic quantum computing. And yeah, I don't want to take too much time. So
Constantin?
Yes, hello everyone. So, is it working? Yeah. So yes, I work at Pasqal, and my job is leading the efforts in understanding how good what we can do on the QPU is compared to classical methods. So you can feel that there's some quantum advantage in there. And naturally, one of the metrics that we look at is energy. So that's why it was very interesting for me to come to this conference to discuss this topic.
Tristan? It's by order of age, if you want to know. More or less.
Thank you, Olivier. So I'm Tristan Meunier. What I'm doing...
Just more or less.
So I'm working. Actually I was signing my contract yesterday actually in Quobly.
With whom? Oh, Quobly.
With Quobly, yeah, because
okay.
You know, before I was researcher at CNRS, and now I moved. And
you're full time Quobly now?
Yeah. So I will be able to answer one of your questions: the transition from academics to industry.
Yeah.
Basically, I am like the kind of the guy to give.
We'll see in 2 years, but.
And so what I'm doing, I am the CTO, so I don't know exactly what does that mean, but this is because I'm coming from the academic world, but I lead the quantum effort. So I am like in Quobly we have like 2 pillars, which is based on technology with the semiconductor industry, and another pillar which is quantum physics, and my background and my expertise are in this domain of manipulating spins in these transistor-like structures. The goal of Quobly is to use what we learn from like the best system to build classical computer and try to build a quantum computer with it. And so this is my.
Okie dokie. Now we have Pierre.
Forcément. Hi everyone. Then Pierre, working for IBM. I'm one of the technical director in France for IBM, and I transitioned to quantum computing 3 years ago after 18 years. I think this year, 18 years in IBM. Then no one is perfect, but I know a lot about classical computing. That's all of my career, and then quantum is just a new stuff for me. 3 years and moving from an HPC background. I'm doing most of my careers in HPC and informatique de gestion, let's say the large mainframe that make IBM a powerful company.
Last but not least.
Thank you. So Joseph Michael, I'm leading the quantum effort at EDF. So most of our work is to try developing some algorithm on machine learning, of course, partial differential equations, combinatorial optimization, material science, and I think I forgot a couple of them. And besides, I'm coordinating the OSQ project with Alice and Bob, Quandela and CNRS.
I'm going to continue with you. What's the role of this topic, the energetics of quantum computing, or maybe beyond computing, I don't know, telecommunications to some point, you think in the ecosystem first and in your organization second?
So
even though you talked about it in your presentation.
On the classical side, it was not a topic until recently, very recently. So the figures that I showed before are pretty new, and it's surprising to me that we never plotted the figure of how much does it cost to run a server on an HPC. And the fact that we started to do that last year, is informative because it was not a topic. And when people try to start something, we are always saying to them, okay, don't do that, you'll spend more time to quantify something that is cheap. So now everything has changed for some reason. People, engineers, want to understand how much does it cost to run their server. We have some problems in our data center. Today we can't change for a more powerful HPC because it simply won't fit in our data center. For quantum computing, it's also a topic. It's if you have to feed 10 or 20 megawatts quantum computer, we need a quarter of a nuclear power plant, so we need to know. And the numerical industry, as I tried to show before, is increasing much more faster than expected. And it's always today realistic to imagine that this numerical industry will consume even more energy than the electrical vehicle. And just to mention, we started working on electrical vehicle 20 years ago. We didn't do the same on the numerical industry. So it's a topic.
So we have to make a choice. Either you get a QPU at home or an electric car. It's not the same kind of business. One is a professional business, the other one is consumer.
You need 100 Tesla to provide electricity for one single QPU. So maybe you can
that's
raise
a good
the
number.
two.
Yeah. Pierre, I would like to dig into the story of the connection between the QEI and IBM, because there was a kind of back and forth
Yes.
Larsen effect to some extent.
Yes, something like that. I don't know if it's a Larsen effect, but that was a good
It's an
positive
electronic,
effect.
analog electronic
Yes.
thing.
I think we were part, I mean, I'm not sure, I'm not thinking, I'm sure we were part of the QEI last year in Singapore with Annie Peik, one of our fellow, being part of that. I mean, for those of you that don't know Annie, she is one of the let's say, mother of supraconducting qubits in the US. And she participates last year, but we also have some questions and answers between the QE founders and IBM's leadership, Jay, myself, etc., regarding what's the impact on our way to think about the energy consumption, and we were approaching that at that time because from the classical world, we are winning contracts because of the energy consumption of some of our solutions. And then that's a reality in constrained world. The energy consumption of classic is a way to win contract, but sometimes it's also a way to lose contract. And if you put a lot of effort in quantum computing, and that's exactly the discussion we had 2 years ago, we need to think about what is affordable and what does it mean to be affordable for a quantum computer in terms of energy. But then it translates, I mean, how would you say that? Stupid, economics, stupid.
It's the economy stupid,
Yes,
yeah,
exactly.
Garville.
Then, yes, everything is related at the end to the budget.
It was during the Clinton campaign. So I don't know if you were alive back then, 92.
and I just checked what Joseph said. You were talking about HPC. I think the Green 500, that's a project that was launched in 2007. I mean, that's not that much.
Very late, you mean? Yeah.
Yes, very late. And that's
yeah.
just the beginning of the Green 500. That means that the energy consumption issue is something very new. It was absolutely not. And that's a good stuff that the quantum world is taking that in advance.
16 years after the top 500.
Yes.
Well, I remember the Cray one. It was a marvelous machine in '76. So, Pierre-Emmanuel, probably you have some stuff to talk about photons and the magic of photons over there.
Yeah, I think like for us, it's a very natural topic to be in. I mean, myself as a scientist, I think this is a very interesting question, quite a relatively new question in the quantum computing community. And so, because it's a new question, it's very exciting to be working in this. And for the company, I think it's very interesting because, you know, like we tend to say photon is a good technology if you want to be energy efficient, but it's just a claim, you know, and I want to be able to formally say it and to formalize this question. And I think this kind of initiative is a good way to formalize and make sure that the claims that we could make are robust and sane, basically.
What do you mean it's a definition of marketing? You got a claim and then you create the product that matches the claim?
No, I mean, it's not something we are claiming from the marketing department, because I'm just keeping the idea in the science department for now. But it's an idea that has been in the air, at least. And so it's good to be able to do some solid work in this before the marketing department takes grip of this.
You
it's
know,
actually
when those startups are created, the marketing department doesn't exist usually. It's a bunch of engineers and
but actually,
researchers.
I was in Munich and there was a talk from someone. I'm not going to give out names, but the headline of the talk was energy efficiency of some platform, and I was like, "What's behind the claim?" And the answer was just, "It's marketing." So I prefer to do the converse, like do good science on this before it goes to the marketing department.
That was the role of QEI to some extent, yeah, to rationalize a little bit those claims. Tristan, what do you do? Spins, yeah.
So the proximity of the QEI founders was one part of our interest in this
You mean
question.
the Grenoble ecosystem?
Yeah, Grenoble ecosystem, Alexia Ofeb, and also you.
No, I'm not in Grenoble. Robert is in Grenoble.
Yeah, no, but I mean this the proximity of these people that this is from one side. But I want to stress that our technology, like the FDSOI, was very advanced in this type of questions for classical computers. And I think the transistors of FDSOI, and there is a lot of engineers that we are working with that are trying to shift, so to give you an idea, to shift pretty much the voltage that you apply on a computer in order to decrease as much as possible the consumption of the electronic systems. And especially if you want to, I remember some talks at IEDM where they want to put some circuits inside their glasses in order to change a little bit, to have like active glasses, and they wanted to reduce as much as possible the consumption. And this is the idea behind the FDSOI, where you can shift a little bit the transistor working point. And so this raises some interesting questions, and we have like a bunch of engineers that are working on these topics, and we benefit from these two sides. The side from the quantum, where there is fundamental questions, but there are fundamental questions, but there are also like some more practical questions, but also from the engineering side, because when the scale is going to be important, and this is going to be a matter, and I think that in this situation, our system, due to the miniaturization, with all the control, with the fact that we need to be sensitive at very, very small signal, this is going in the right direction to tackle this type of problem, and this is a subject that has been already tackled by the classical engineering community.
And you were also involved in many collaborative projects like Riolink and so on, where the energetics was right away 2 years ago. It started.
No. For us, I think that the first time that we had like a European project with Alexia, Rob, and I think I saw, I don't remember your name. This is Constantina. That was like in QLS side. This was 4 years ago, in 2020, and we started to think about these ideas with Alexia back to the emergence of the quantums ideas around, and together not only like quantum physicists that were interesting to Maxwell Demond and all this stuff that are very much interesting in this fundamental physics, but also like to have like engineers from Leti that are that knows how to basically calculate what is the effect to run some current, to charge capacitance within these systems, and we use exactly the same type of process in quantum computers, so that's why it is interesting.
Constantin? You're famous for the hair dryers.
Yes, exactly. So I was about to mention it. Can you hear me? Yes. So it's true that one of the main differences between neutral atom technology and superconducting qubits, for example, is that you don't need a dilution fridge or like cryogenic setups. So at the beginning of Pascal,
you still need a 4K compressor.
Exactly. Yeah. So at some point you need to create some vacuum. So it's
fact checker.
You need some. You need some energy to do this. But one of the claims was that once you've prepared your vacuum chamber and you let your atoms evolve, you're kind of working at room temperature. And so one of the first arguments was that we heard from our CEO, for example, was to say that you consume much less energy than superconducting qubits. So the image he had was you use the equivalent of 4 hair dryers, which I thought was a bit weird of a metaphor, except if you're a hairdresser, I guess. But it was showing that you're hopefully using less energy, and with the number of qubits, you don't see a huge increase in the energy. So you can go up to 1,000 qubits without modifying the energy consumption, and even if you go to bigger system sizes, you still it will still be contained quite well. But now after this, so there was this this hackathon, which is called the it was a Blaise Pascal, I think, hackathon, and it was really trying to understand what you can do in the domain of energy. And I think now in turn, what I've showed in my presentation was that we're trying to understand really in practice how much we consume in energy when we're running algorithms on our QPU. And we're trying to do this in the most honest way. And of course, maybe we're not doing we are trying to have the best metric possible. So that's why I think it's an important question at Pascal.
By the way, I will remind you that you will have your own questions, so get ready. No, I'm not the only one asking questions. I have a laundry list of questions, but you can ask your questions when I'm finishing the kind of the preparation I had. Tristan, same question? No, you were there. Sorry, I'm confused. Who's missing? Oh, Giuseppe, yeah. About the question about how it's changing your organization work. What's interesting is probably on top of Joseph, as a vendor, you're the only one looking at different platforms. So is it in different? Yeah, he's working with database and analog. So does it mean that it enables you to do better comparisons for the energetic standpoint?
Yeah, exactly. So I think we have had this energetic topic in mind since the beginning, since we are connected also to HPC. So we are also very connected to HPC. And recently we moved our lab to a new location. And since then we have started installing some devices to measure the actual energy consumption of all our devices in the lab. So now we can monitor in real time the consumption of all the parts of our lab. So the cryogenics, control electronics, etc. So this will allow us to, we already have some preliminary benchmarks. So since we have connections with HPC, we have energy metrics from the running of simulations on the Barcelona Supercomputing Center. So we can, I think we will be able to benchmark, have a good benchmark between different platforms and with a classical, and as you were saying, we have gate-based and analog devices, so we will be able to perform this comparison.
Another one I have for all of you, maybe start with Joseph and Pierre. How is this energetic thing, particularly coming from the bad news on AI, changing the way you do R&D on its own? Is it changing somewhat more or less the organization, the kinds of people you hire, the way you arrange projects, or is it just one topic on top of others, like a new metric popping up somewhere? Who starts?
Thank you.
You need to compile first, yeah. You're a user, it's a different thing. But,
I can give you two levels of answers. So how is it changing the business at EDF? It will change stuff because, of course, as I said, we provide energy for data centers, and we didn't expect that. Within my team, I'd say that we aim at entering in what we call a responsible numeric use, which include a lot of things around privacy. And now energy is one of the other things, pretty new other things. I'd say it's kind of a new metric that we had now systematically when we do some comparison between quantum and classical, so we do it at least internally. That has driven us to try to understand better how we can optimize energy usage of our HPC. So now we are in a position where we optimize the usage of the HPC. Does it change the whole organization? For now,
maybe not the whole one. I mean, mostly on R&D. I mean, and even the skills you need to some extent.
Now, I can say that it is now a systematic metric, and it's pretty new.
A new metric, okay. Pierre Emmanuel?
Yes.
You could compile.
Oh yeah, I compile. Slowly, but yes. From a business standpoint, we did not wait for the customer to put that in place from a quantum but global company point of view. And as I said in my introduction, it is a way now to win contract when you have the less, as Constantin said, the less solution the more powerful solution in terms of energy consumption. I'm not sure if I'm clear, but let's say best storage capabilities for the less energy, best compute capabilities for the less energy, etc., etc. It's a way to win market. Second point,
in the classical world.
In the classical world, then it is obviously the case also in the quantum world. That's just the same. Second point is that there is legal criteria that are ongoing the ESG criteria, which will and are arriving in the market right now. That means that customers need to measure and track their energy consumption, and they need to report that with the same accuracy that they do for the financial reporting. And then the best sellers of one of the best sellers of 2024 for IBM globally is sustainable software that take part of that. And then we will be very stupid if we do not think in our R&D process about something that is a demand about our customers globally. That's just pure adaptation to the market. Last, I will answer the same way that Joseph answered. From an organization standpoint in our R&D team, it doesn't change that much. It's just having energy at the bottom of any decision making that you can make when you design the system. We do industrial quantum computer. That means that if at the end for every quantum computer we want to sell, we need to put a nuclear plant, that will be good for Joseph, that will not be good for our sales. then that's very basic stuff. That means but that's the same for security by design in the code. No one could answer that security is not part of the day-to-day software development. Yep. That's the same for energy optimization.
That may explain why companies like Google and Microsoft and others, they do fund or have specific procurement for energy sources, like the 3 Mile Island thing with Microsoft and the Google 1 gigawatt that was mentioned, I think, before. So they plan in advance, just for AI, not quantum. Yeah. Pierre-Emmanuel, maybe? Oh, Joseph, you wanted to add
just to
something?
Comment, because I compiled after you.
Yep.
Just
they're all working in batch mode.
Today we can't sell a new project internally if it doesn't show an energetical advantage, or if it doesn't show that it has an energetical benefit within the company.
So it's going to be a criteria for selecting.
EDF, and it's also the case for a couple of banks that are new and a couple of other company. And today, when we buy an HPC, it's one of the big metrics that we consider.
And so for Pierre-Emmanuel, Joseph, and Constantin, your 3 startups, I mean, the largest one is this one. You're 300 people, about 100. How many are you? 55, so different size. So is there a connection between the size of the company and the fact that somebody works on this energetic thing? More or less?
I don't know. That's a good question. I guess not. It's mostly like if the company thinks it's an interesting topic, people are going to work on this regardless of the size of the teams. And I guess regarding the question you ask, I mean, I would be lying if I said that the energetics became the one topic in Qandela overnight. Of course, we still have very difficult questions regarding fault-tolerant architectures, algorithms, device theory, and also like a lot of hardware work to do. But it's really an important topic, and I mean, we recruited Ariane full-time for this topic.
That's good.
Yeah. So yeah, it is impacting the company, I'd say.
Constantin? He's a startup as well, I forgot, but he's got the COA and CNRs behind him. That's maybe a big difference.
So I'd say in our case, the demand for studying energetic consumption came from the top of the company. So it came quite quickly, I'd say, and not really related to the size. It was always an important.
You have one guy in the company named Alain Aspect. He's talking about that in any presentation. Yeah.
Yes. Yeah. Absolutely. Yeah. So no, it's a topic that we've been following for a long time. But I think really doing the metrics, it takes, as Pierre said, for Qandela, it's exactly the same for us. We have a lot of work to do in many different domains, and energy now is part of it. But I think we also have maybe we have one person full time on it.
Cool. But it's a very different topic compared to, I mean, a specific algorithm design or QEC, whatever. It's very transversal. So you need to have people who look at all the aspects of the technology from top to bottom, or bottom to bottom up. So both of you now,
Yeah, so what I want to say about our technology is that we are extremely inefficient.
Inefficient.
In terms of like how we excite the spin and everything. And this is true, I think that everybody has to know that we attenuate the signal quite a lot in our signal, right? So this is true for superconducting qubits, this is true for us. And so I calculated just to have an idea because I didn't want to put, but we usually use 100 dB attenuation. So we put 1 volt on top of the fridge and we have like 100 microvolt at the so yeah, so there is a lot of room of improvement for our systems, and this boils down to the cryoelectronics that we have in our system. So yes, we do that because we have a lot of gain, and it's not only related to the fact that this is better, it's also going to be cheaper. And usually, like this energetic problem, I usually like connected to the not only to this energy problem, but also to the costs that is going to happen. And for Quobly, this is clearly like a driving force to have like an efficient and as far as energy, but also as far as cost is concerned, to provide this solution like optimized, so to speak. And our connection to the semiconductor industry helps us a lot on this subject. But this is a driving force for the R&D via the study of these cryoelectronic systems that we have.
I can testify about that because I've known you for some time, but I remember 4 years ago you were already starting to think about cryo-CMOS and the way you drive the qubits and find the efficiencies, because there's a lot of trade-offs there between the cabling and the cryo-CMOS and the cooling.
But don't remember the fact that nowadays what is limiting us is not at all the QPU, right? It's the infrastructures.
Exactly.
Right? So we have a dilution fridge. This dilution fridge is overwhelming, and even if you use a 4K thing, is overwhelming any kind of like a signal generation that you have. But this is true for just a little time, right? When the thing is going to grow, at some point, as the classical computers are not limited by the energy for the fan, but this is limited by the dissipation from the circuits. So, but the system has to grow for that. And for the moment, we are not limited, so this is not a very crucial question for the moment, because we need to have like this system at low temperature. But as the system grows, it will become more and more important.
Joseph, some feeling about that?
Thank you.
You've worked a lot on the software aspect of that in your studies.
So yeah, as I said, this topic was interesting for us since the beginning. But yeah, when you start, well, I didn't start it, but when the startup starts, you have few people that work in many topics. So maybe there's one people working on this, but he's also working on 5 other topics. But yeah, now at the level we are, we have one person who's full-time on this topic, and some of others maybe in some projects also participate. Yeah, and it's a topic that will put more efforts in the future. So yeah.
Okay. Another question is the tooling for looking at the energetics. What kind of tools do you need? I mean, there are some initiatives. You have the IEEE working group driven by Alexia and Marco Felus. There are other initiatives driven, at least in France, by Frédéric Barbaresco on the BAC project on benchmarking, including benchmarking in energetics. You've got the QBI initiative in the UK with DARPA. Do you think the ongoing work on standardizing and benchmarking is enough, or would you need more tools to look at this topic from the R&D standpoint? At some point, it becomes a marketing point, but at the beginning, it's a scientific issue. Pierre, don't let him compile.
I was trying to compile again. I think the way I'm seeing the problem, let's assume that we have a problem that we want to fix. That's maybe not sure, but let's assume that. The way I see that is that if we want to do fair comparison apple to apple in terms of energy consumption, it should be seen from an application standpoint, maybe not from an end-to-end application standpoint, because and that means we will have to think about the overall chain. But I think that's what in reality, what we see in the ESG criteria, scope 1, scope 2, scope 3, what I'm doing, producing myself in terms of energy, what I'm doing, let's say the people that are working with me and the people that are working with me. And I think from a quantum standpoint, the question is do we want to fine-tune and have global metrics for every, I don't know, the consumption of one gate on the technology? I think we maybe don't care. The question is much more from an application standpoint. What is the consumption overall? And I forget the name, but one of the speaker this afternoon explained about the VQE. We know that VQE and other algorithms are coming back and forth with classical and quantum. That means that quantum is not somewhere in the air and doing something alone. It's connected to the IT system. It's connected to the overall system. And the question is, from a customer standpoint, the end-to-end. From a quantum provider standpoint, I will end at the end of the QPU, but should I include the SDK and all the transpilation, etc.? Definitely yes. That's
so
an open question.
Is it making a comparison difficult between hybrid solution, which it's always hybrid, I mean, and the pure classical solution?
Let's take the same question on the AI world.
Yep.
Are we sure? I mean, we have the spec of the last GPU, and I can give you the spec of the last QPU of IBM. That's very easy stuff. That's what, and that's it. You got the power. But at the end, what can you do with that, and what it translates in your real floating point 64 calculation with EDP? That's totally something different.
Pierre-Emmanuel, ideas on that?
Yeah, I think, well, to me, the initiatives we have are really like fueling the scientific discussion. So this IEEE standards that you mentioned, I'm also involved, and I think it's very nice. Like we have a lot of discussions. Of course, it's very hard to come up with the standards, but like we are trying to do our best, right? But then, of course, yeah, I guess a lot of things are missing, but it's mostly like scientific considerations and more work to do, and that's coming, right?
Others, ideas, tools, metrics, whatever?
So I feel like in classical computing, there's a bit more standardization and consensus on the metrics to use, for instance, flops or this kind of metrics. And in quantum computing, when you want to compare it with quantum computing, is a bit more difficult. Because the operations that classical and quantum computers make are not the same. So it's difficult to have a shared metric between them. But not only that, but also inside the quantum computing devices, it's difficult to compare them. Because you have different technologies, have different paradigms. And also the algorithms are very related to the type of hardware that you have. It's not the same quantum annealing algorithm, which runs in an analog device, and a gate-based algorithm. So most probably this benchmark will depend on as he was saying, on the applications. Having a benchmark, a metric for a general purpose quantum computer might be more difficult. So I think we should push to try to design a metric, an agnostic metric that can be applied to different technologies. And there's also many factors that can affect your performance. Number of qubits, the coherence time, connectivity. So yeah, it would depend a lot on what do you want to solve.
Yeah, what's going to be difficult is that it's much harder to compare even QPUs altogether before comparing it with classical systems. You have different paradigms, like Coral presented this morning. And so is it making your life more difficult to analyze the energy consumption?
For instance, we are looking at proposals for metrics, but see that most of them are for gate-based devices. So we have to find how to apply them to analog devices. So yeah, for us it's important to find an agnostic metric that can be applied to different technologies.
It's same for you. You have to compare air dryers and ovens, whatever.
Yeah, it's true, and also the standardization is a difficult task in general. Like if you think of, for example, quantum volume metric.
It doesn't work with you.
Right, it doesn't work with us. It's always when you're trying to find something universal to describe many different things, you're obviously going to have a trade-off of what you're measuring. So I find it very difficult to do standardization, but it's a very cool effort.
Tristan, ideas?
No, the same thing. I think the effort is within each technology. I was thinking like when I basically discuss this type of questions, my reality is very different. I don't use this very maybe high power laser that you use. This is very, very much different. And I think all the work of optimization, so to speak, is happening nowadays in the company. And this is a crucial question because it reduces again the cost if you do that correctly. I'm not sure about like this idea about like metrics because for me just like it's very easy to ask EDF to give me like what is the cost for a specific task. For me, this is like this is the metrics, right? I do a task, you do a task. I just ask EDF. EDF show me like the bill, and that's it. So, but this has to be like the similar task, okay? And then if you compare where we are, like we have like very, we are at the beginning of the race, lagging behind in terms of the number of qubits. And if you compare with like Pascal or IBM that are working with thousands of qubits, yeah, this is very difficult to compare.
Not that much.
No, it depends. It depends on. I like this. This is fantastic work. So this is, but that costs much. That costs more. Okay. So, so for me, this metrics is, it's good. It's a good metric for me.
Okay. I would like to bump and to follow up on Coral's presentation this morning. Could you get into more technical details on what is specific in quantum software and top to bottom, I mean from the algorithm itself, compilers, optimizers, then QEC and even firmware. So where do you think there's a big difference between classical computing and quantum computing, and how is it? Yeah, it's your exam. You've got a jury over there. You want me to design, to say who's going to start? Huh? You mean me? You mean is the scapegoat? Oh yes.
So,
okay.
So the question is, what is different in terms of energy?
Yep.
No. So what is the bottleneck, right?
My question was, what is different between classical world and quantum in the software stacks and its impact on energy?
In the software stack?
Because the optimizations may be at different places. I don't know. There are so many different things between classical computing and quantum computing. I wonder where is the difference in the cost, the energetic cost of this.
In the energetical cost?
Yep.
Yeah. What I can tell you is that, of course, classical computing is very mature, and quantum computing is not. Tristan told about some microwaves that are attenuated, and there's a lot of optimizations that are not being.
It's not software.
No, it's not software, but
okay.
At the end of the day, it has to be optimized somewhere.
Yeah.
Regarding the software, we do have now some software that that help us reducing the electrical bill. So when we compile, we can input some condition to reduce the electrical bill. When we run some code on HPC, we can reduce. So the user can accept to increase the computational time of 10%, I don't know, to reduce the electrical bill. So it's very mature. We don't have that. I don't know, but I'm not sure we have a transpiler or nor a compiler on the quantum computing side, which tells us, okay, I will increase the computational time, or I don't know, but your precision will be lower down, but you have a lower electrical bill.
We had this problem this morning about the level of abstractions you have in languages. We don't have the equivalent of, let's say, COBOL with a Q, or Python, which is very heavy, and then microassembler or C. We don't have that gap in quantum computing right now. So it may change in the future.
What we do have is firmware stack.
Yep.
Provided by the hardware providers. Yeah. We have the frontware stack provided by Qiskit, for example, and Pulsar and no.
Pulsar is over there.
Perceval. But in the middleware, what do you have? It's a question. It's an open question. Of course, IBM is putting an effort, but I see a big miss here, and I guess it's one of the difference.
Interestingly, in the IBM case, all the work you do in Qiskit is amazing because sometimes you give the impression that you multiply by several orders of magnitude the performance. I mean, if you get the clocks, the famous clocks, the cycle layers per second, it moved from 4K to 200K. Yeah. So what's the magic behind that, which is software-based?
It's software optimization.
Yep.
Mainly, the magic is not new. I mean, that's something that was invited in the beginning of the IT, but that's a lot of people forget because of the cloud, all-you-can-eat stuff. I mean, you just go, you click, you have your virtual machine, and you can compute whatever you can, and you don't care about your memory. But if we think about the quantum space right now, what we do is software optimization, and it could be very easy. I think at the beginning of Qiskit, everything was in Python, which is quite inefficient. Mm-hmm. And then I think that right now, I don't know the exact number, but the vast majority of Qiskit is in Rust. And it's a tremendous change in terms of how is it compiling, transpiling, fast or not. That's we apply the same stuff, for example, to the internals and to the way the mechanism of the speed of the hardware is working. That's software optimization. That's also better knowledge of how our system will react. That's the constant stuff. After that, we love to say that we hired a lot of very good software engineering people, and we want to hire more. And the challenge in software engineering and algorithm, as your work, very important. I think that's yesterday one of our quantum network members, Ion, announced a 40% decrease of the numbers of gates of a quantum machine learning algorithm. Does it make that quantum advantage? Not. Mm-hmm. I'm clear. But is it the way that we all should think about quantum algorithm? Yes. How do I minimize the number of gates? Why is it important? Because I have, on the other hand, hardware that is limited in terms of number of gates that can execute before having a random number generators, which we don't have. We have real quantum computers that do real tasks, even if some people forget that.
Yeah, but by the way, there was a recent phenomenon, I think it started 2 years ago, where some companies like Eviden and Intel, they chose to enable the development of software code with C++ instead of Python, which is not efficient. So it's about the other way around than usually we, in the history of classical computing, we went from machine language, blah, 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 up C, C++, then PHP, whatever, and this is going down, which is a good news for performance issues. Guys, any ideas on that? Software? You do hardware.
It's a very difficult question, no? This is incredible. This was not written on the text.
No, it's my backup questions.
No, this was not written. And we need preparation
it's
for
a
that.
Trap.
Right?
It's a trap. It's a trap. That makes it fun, yeah. Or not, it depends. Constantin, any ideas?
Yeah, so on our side, there's very little like the stacks of software. It's mainly when you're in an analog mode, It's mainly to do the control of your lasers, of the different elements of your hardware. So I wouldn't say, I'm not sure it consumes much energy to just control your parameters of on the device. But it's true that I would be very interested in this when you go to fault tolerance and you build your different codes of corrections. Yes, what's the biggest, like usually in code you have this 80%, 20% rule, where 80% of the time spent is taken by 20% of your
But if I'm
your
not
code.
wrong, in the analog mode, in your case, and even in D-Wave, you need to use a kind of embedding system that converts a problem, let's say a QBO, into the native BQ and whatever that's supported in D-Wave, and it's the same for you. So is it had a cost? Is it got a huge cost, particularly at scale?
Yeah, I'm not sure.
Yeah.
I don't have
You know,
the
we
answer
don't
to
know
this
yet,
question.
yeah.
We don't know yet.
Yeah.
When you get to big sizes, yes.
Yeah. You don't know? Yeah. You don't do analog, so you don't care. Not yet.
But this is the same problem for FTQC. You know, this
FTQC,
type of,
yeah.
This is the same problem. You can basically compile how much effort do you need to do on a classical computer to I don't know what you call that, but to translate into the order that you send to the quantum computer. And I think that this is like still to look after. I think we need to look for that.
In the case of Quandela, you have Percival, so your own software tool. It's a different model, I would say, to some extent. You've got the KLI model and dual rail, and then you've got the future FBQC model. So are your existing and future hardware architecture going to have an impact on the overhead of software? When I mean software, I mean the software tools, not the algorithms itself.
Yeah, I mean, yes, of course, it's going to play a role. Like, for instance, if you go to the FTQC regime, one particular problem that we want to consider in work, actually, but it's very hard, is the decoding problem.
Yeah.
So for the decoding problem, it's very tricky because it's a difficult problem that you sometimes have to consider close to your quantum system, and close might mean within the cryostat, if you have one. And then the question is, it's going to bring you a huge energy cost if you do that. So can you take it into account, and how do you reduce this cost to the minimum? So this is one example where you need a lot of software optimization to make sure that you're not consuming too much energy if you want to do this.
So the three of you, so Joseph, you and not Constantin, who am I missing? And Jeremy is over there? Jeremy Stevens. Oh, he left, okay.
We have Axel representing Alice and Bob.
Yes, you're from Alice and Bob. So you are all involved in this OECQ project, but for the others, what would be for you the potential needs from the academic world to address that energetic question? So, because you have a couple academics in the room here. Hey, listen.
Yeah, I have to go.
Oh, he's got to go.
Yeah.
So we won't have.
It's not a question for me, so fine.
It depends. Yes. Okay. Thank you, Constantin. So, any idea of what the academic? Yeah, we can applaud him. Yeah. Thanks a lot. Any idea of what how the academic world could contribute, and maybe in an innovative way? Because we know it's hard. I mean, the academic world doesn't work the same way as the R&D within companies. So, what could be invented as a kind of modus operandi to address that new issue?
Yeah, I mean, I don't have specific questions, research question in mind, but I think what's really nice about this topic is it's, as I said earlier, it's a very new topic. It's recent in the quantum information world, and so when a field is recent, there is a lot of, like, tons of good questions to ask and to answer. So, yeah, as I said, for instance, just before, like the decoding problem, it's going to be an issue, so it's more an algorithmic problem, so it's not like a thermodynamic equation, but it's going to be a huge issue. How do you tackle that? And then, for instance, for photonic, you have a lot of questions regarding the energy consumption of the device, and how do you model it, even, which is a tricky question. And so it's really a research question. So that's why Ariane was hired, and like she's an expert in thermodynamics of photons. So this is really, academic type questions.
And would you say that? Oh, Tristan, you want to?
Yeah. So for us, we have like a lot of questions regarding like the thermal exchange.
Yep.
Which is happening within our device, and I think that. But I know some of the work that of Robert or for other from the academic world. To extract how the phonons are going to be extracted to keep the qubit cold, but also like to manage a little bit, to be efficient in the way that we thermalize, to avoid eating too much and dissipate too much. So I think that there are like a lot of questions that are addressed nowadays that are more on the classical side, I would say. And this is more like thermodynamics, old school thermodynamics that we are like pursuing in different collaborations that are extremely important to maintain the qubit cold and also to control the dissipation. So this is where you have active device. And here there are like a bunch of questions that are not addressed by the semiconductor industry, because this is not the same regime of manipulation and control. And that is where basically the academic world is strong, from the engineering side, but also like when it is going, I saw like Robert nodding, but this phonon, the way that basically you can keep and extract the phonon hits, I think this is extremely important for us.
And how about partnerships with the upper layers? I mean, the software engineering stacks, because there are specialized people in that space, in INRIA in France and elsewhere, in Fraunhofer in Germany.
In software for...
Software engineering. I mean, I was in Munich 3 months ago. The team from Robert Will is working on a lot of software engineering things, which may have an impact on how you estimate your sources, on software, you do optimizations. As part of the QEI, as a community, I've seen much. I mean, the work was focused on I would say, the physics level, like you mentioned. But what I'm wondering is what could be done potentially on the upper layers and the software engineering. And particularly, we didn't talk much about QEC, but the cost of QEC in the energetic is huge. And so should we invent new partnerships with the folks who are inventing QEC? And QEC is connected to the circuit design and non-local connectivity and stuff like that. So can we invent something new to some extent? Photons is easy, no?
I can try to answer. Like, so for instance, I mean, the architecture is going to play a central role. And then the architecture is something you can invent at will, almost. I mean, it should still do quantum computation in the end, but... And so if you look at photonics, for instance, one of the first like good proposal for an architecture which is fault tolerant is the one from Quantum, fusion-based quantum computation. And if you look at the details, energetically it's going to be quite a huge consumption.
It was on the left of my chart.
So it's not something that they're afraid of. They're actually like intensely working on how do you dissipate 100 watts at 4 Kelvin, which is huge. Nowadays it's mostly 1 watt at 4 Kelvin. So it's a huge difference. So they're actively working on that, and they are not afraid to do so. But to me, it's not really energetic friendly, right? And so it's so if you look at so we published a paper and a second version not too long ago, where the architecture is different, and I won't pronounce myself on the energetic consumption because it's a work that we have to do, and it's quite difficult to do, but at least just on the resource level, so like kind of the number of single photons you need, etc., it's much more economic to use the schemes we developed. So the architecture is going to play a huge role on the energy consumption, and it's something that you can change and adapt. But then the question is the energy like still it should be fault tolerant, right? So you still need a reliable scheme, and I guess the first question will be how performant it will be, like in terms of thresholds, in terms of number of qubits you need, and okay, probably in a second time, then you can ask the question of energy consumption for this.
Could we start playing the game of the audience questions? We have a mic over there. Do you have any questions? Otherwise, I've got my own, but yeah, Aurora.
So, I'm sorry, we have one mic, so.
So one quite open question for everyone, maybe a little bit hard because it's open. What's for you the major roadblock in quantum computing for your respective use cases? Like if you're a startup trying to build a quantum computer, the blocking point will likely be in building the quantum computer. If you're EDF, it's maybe on the applications or maybe on I don't know, it can be either financing, you don't have enough money to build your quantum computer, or it can be recruiting. Do you have something in mind, like the main thing that you're missing in order to...
Related to energetics or overall?
Oh, it was mostly overall, okay. Sorry. But energetics can, I mean, it's part of the picture.
Okay. Armstrong, Graham, Pierre, no, Joseph.
No, it's easier for me, guys, because of I will say that the major bottleneck is same, but no kidding. The point is that we have to wait still, and we started a long time ago. I still have to wait, and reasonably, I still have to wait. I don't know what's your opinion on that. About 3 or 4 years to get some value or to get some beginning of something. Keeping the momentum in the company is not an easy task from a day to another. And it's not just that, it's not only I have to keep the momentum, but I have to increase the momentum. Because today I'm not ready to use, 10,000 logical qubits. Just not ready because we have a couple of different hurdles to overcome, algorithmically speaking.
That's why we're waiting to do that.
But it's not only a matter of hardware, but it's also a matter of algorithm. And this is the kind of thing that only us can do because we know our use cases, we know what's important or not. And increasing the momentum to get some beginning of value in 4 years, it's not an easy task in a company.
I think we could separate your question in 2 different answers. The first answer is QPU provider. I will assume that we don't see huge roadblocks. We see challenge, and we see a lot of work to do. But it's much more like Lego. We have an error correction code, QLDPC, that we think will work. We have 6-way connectivities. We have stable qubits. Are they the best in terms of stability? Maybe not, but stable enough. Could we win other order of magnitude from a quality standpoint? Yes. Could we put that in a large cryostar? Maybe yes. If other partners, that could be a link to the first question of Olivier, previous question of Olivier, do their work. Then from a QPU standpoint, it's much more engineering, standardization, lower the cost, and no critical roadblock, but a lot of work to do and a lot of reason to fail. We are confident, but on the other side, there is one stuff that keeps us awake at night is, are we really putting enough effort in the algorithm development and in the algorithm optimization? Let's say that how many times researchers, coming back to your previous question, Olivier, again, how many times researchers spend on optimize the current algorithm that we know, to not say, I will take something that we need millions of qubits and that's perfect, but say, what's the reality of the roadmap of all the gentlemen until 2030, and then what should I do to my algorithm to adapt to this roadmap? And that's a place that a lot of people try to forget. And that's, for me, the largest roadblock.
Any other? Tristan? No roadblocks.
No roadblocks. Yeah, I think that I would say the same thing as Pierre. Yeah, so we are like we have many challenges all the way, and in Quobly we think that this is good, this beginning of a quantum computer, but the real application is going to be large scale, and there is like many challenges to tackle. But you know, we use technology that are very much connected to the technology used with classical machines. So we want to leverage that as much as we can, and so we need to accelerate on that, of course, and to have some good people to do that. I think for us, it's really like you know, I was in Taiwan. You know, very recently, and I realized that TSMC is not at all like putting any effort in quantum computer.
Oh, they have a team looking at this.
Yeah, no,
small
but
ones,
you know, it is, and you know why? You know why they are? You know, this Taiwan island was basically like, for me, this is the semiconductor island. This is going to be like the largest, and you know why? Maybe because they have a large market, right? To you know, they don't want to spend anything on quantum. Right, and so the roadblocks for the moment is that we have like this moving target, which is basically classical HPC, which is basically making a lot of improvement as well, and so people from that community can help, and they are like, you know, we have one example of this type of profile that are now within the quantum community, but we need more of these people to come to our business in order to give to us the knowledge to build the machine. In other words, this is not going to be physicists like me that is going to build the machine. This is really like engineer people like with HPC. And this is where we need to have like some people coming from like a very active community, and 10% of the market worldwide. This is extremely important market for the moment, and I think we are very little. And we need to convince people that we have like a very good shot at what we are claiming.
I had a big surprise in July. I was in Lindau in an event where they had 37 Nobel laureates, and I asked the question to David Wineland and to Bill Phillips and Alain Aspect about whether the challenges those guys have is a scientific challenge or an engineering or technology development challenge. They all say, and they are scientists, that it's engineering. And, well, being halfway between being an engineer and scientist, I believe there's a lot of scientific challenges still there. So how would you rate the scientific challenges around? There are still many, I mean, both in software, physics, hardware. I mean, one I like is correlated noise, which is an unknown, I would say, zone. So how would you rate those challenges? And maybe they relate to the energetics to some point of those systems. No? It was not planned, so I'm sorry.
No, I don't know. I kind of agree with what you say. Like, it's some sort of an engineering problem. Like, we identify what needs to be done, the points that we need to work a lot on. So it almost sounds like an engineering problem, but at the end of the day, we also have like science questions, non-trivial science questions. For instance, for single photons, we'd like to call what we have like deterministic source of single photons, but it's not deterministic at all. And we lose a lot of photons when you just excite the quantum dot to get a single photon out of that. And theoretically, you can get to 100% brightness, almost. So there is no theoretical blocking point to this. So you could say it's an engineering question just to make better sources. Okay, but for now it's in a research lab. It's not in a production fab, right? So it's still a research question to make better sources, for instance.
Yeah, maybe.
Okay, so we have many challenges in all layers, from hardware to applications. And I think are both scientific and engineering challenges. So for the scientific part, we are very connected to academia. So we have many industrial PhDs in our company, and also our founders are in academia. And so we try to attend all the conferences that we can and keep ourselves updated about everything new in the field. And yeah, for the engineering part, and responding to his question, yeah, it's also difficult sometimes to find expert in a very specific topic. So yeah, we would like to hire many people that are expert in exactly what we are doing, but sometimes it's difficult to find that expertise in the field.
Robert, you are the next one.
Actually, that last response was a perfect transition because the question I wanted to ask was about recruitment and the sorts of people you need. And also maybe a more general question about the difference between academic research and industrial R&D in this domain where it's quite maybe much closer than in certain other domains, but I don't know. That's what I guess many of you come from academia. Maybe all of you were. So you've probably all made that transition at some point. And I guess that so. Broadly speaking, as I have the list of all of the participants, I know almost everyone in the room is someone who is in academia and knows about quantum. That's more or less the profile, and we should maybe try and broaden the profile at future events. But so I'm interested to know if you have a particular feeling about what it's like to make the transition, the benefits, the disadvantages, what you're looking for in terms of people you might be wanting to recruit, who might be in this room, or the students of people who are in this room. Okay, so I leave you some time to think, and now I stop talking.
So you don't start with Pierre. You have to compile. So, Joseph.
Faster processor.
And there are co-processors, actually. Yeah. Who's the GPU? Who's the CPU? That's the thing.
Thank you for the question, for the event. Compiling. No, it's true that until now, there was a kind of Chinese wall between the academic world and the industrial world, and it's no longer the case. And most of the people who work in the startups or work on quantum in the industry come from the academia. Of course, it's not the same environment. We talked about that yesterday. Of course, you are driven by the applications, by the use case. You can be afraid of the budget reduce. You can be afraid that your project is abandoned from a day to another. So you have a kind of constraints. I also know a couple of students who want to leave the industries to work in academia because they are, of course, more free. There's a kind of prestige around academia. One risk that I see, because the two worlds are communicating with each other, is that the industry can drive the fundamental research. And I think it's not a good idea. You guys have to continue working on fundamental research. We don't have to drive you guys, but we have to meet each other to see if your fundamental research drives us somewhere or not. But I think kind of a risk here where academia is too much driven by the industry. That's for the differences, and if you want to switch now, it's an open bar. So if you guys want to join the industry, I think there's no any concern for a company like mine. But
the current worry is a lot of companies attracting people from the academia, mostly not the other way around. That's what we hear.
And I think it's
and to some point, the discussion on freedom is a complex one because I hear a lot of positive feedback from people who do R&D within organizations, with industry organizations. I don't know the details. You may enlighten us. But
it depends if
yeah.
you need a lab or not.
It depends if you need a lab experiment. It depends also if you are in a narrow topic where it's difficult to get funding from INR in France or elsewhere.
But let me just mention one other thing, is that, of course, we saw a lot of academics coming to the industry. And the opposite has to happen. Because these guys were training the students. And if there are no academic teacher nor students, it will have a problem. So
it's a pipe problem, like we say. Any other feedback?
I can try to give like some answer to Robert that we discussed. I see Thibaut over there. That was one of my students in the class, all right, Thibaut? Yeah. No, this is a young student from like the master course, and he knows that I discussed that a lot during the course also, like this transition between the difference between the two sides. So I think the main transition for me, because I was basically doing this research for very, very long, is the fact that, you know, when I have like a sample, and which is basically like what we construct is something which is unique, right? Most probably the most advanced quantum systems ever produced are nowadays in companies. This is the true thing, and this is fantastic. And from a scientific point of view, there are many questions to address within these systems. Many. But the only thing that matters in an industry is to fulfill like good performances. And so sometimes, basically, I talk to students during my academic life that, oh yeah, this is very, very much interesting, this effect, this new effect that we didn't come up with, right? And that was basically my driving force during the academic world. And now that I am on the other side, I say, oh yes, this is maybe interesting, but this, due to some effects, if it's interesting, this is not enough. Is it useful for the machine that I'm looking at? Okay, this is the first thing in terms of like freedom, and you know, you are not like a little bee to know. After that, from like what I see, and this is like something like from the organization point of view, I think you are less lonely in startups. And so I think that this is really like something that I realize, and I think that rings many bells to some students here. You know, when you are like, when you want to work, and I think about like Oscar, he wants to basically be surrounded by people. He likes to be like with a lot of people around to discuss and everything. And I think for him, like to be in a company, oh yes, you have like meetings, you have like organizations. And that is something that we don't have in like at CNRS. That you are a little bit alone with your like PhD supervisors, and most of the things is pretty much like solitude, right? So solitude in French, huh? And so this is like the difference that I see, and not only like freedom, because freedom, you know, I didn't feel so free during my academic world with all these contracts and everything. I feel a little bit. That you need to be surrounded.
You mean freedom in research? You mean
freedom in research? Exactly. Like this is this little bee, but this is, you know, all my career I was basically like driven by contract and like milestone and deliverables by the European. This is not very much different to what I experienced from what I experienced in Quobly. But the fact that to be surrounded by so many persons and to work as a group and not as individuals, I think that this is. Maybe and to build something bigger by being together, it's really like the driving force in Quobly, and I think on all the community. We cannot do the quantum computing that we want to perform without the help of the others. But that has some constraint. Huh?
Yeah, if I want to join what you said, I think that the goal in a startup is extremely challenging. Like, we are trying to build a fault-tolerant quantum computer. It's very difficult. It's a very hard problem. And you couldn't do it in academia, right, as a PI yourself. So I think it's a driving force, and that's sometimes it's a bit scary, of course. But it's mind-blowing to wake up and try to participate to these efforts. Also, what's interesting. So I mean, of course, coming from academia, a lot of people, you tend to have a lot of discussion on this, even within a startup. And so we realize that, as you said, like when you work in academia, you also have deliverables for your projects, and you tend to have the impulse to write papers because this is how you're judged by the community. You have to write paper to keep alive. In a startup, that may not be the case. Like it's true that your research has to be focused. It has to be focused towards the goals that you're trying to do. So building a fault-tolerant quantum computer. But you don't have to publish, right? So to some extent, you can also do some more risky research. Of course, we are quite free in France, so it might less apply to France. But you can do less risky research, more risky research, because you don't have to publish a paper at the end. Like it's not, if it's inscribed, it says in the startup project, in the goal, then it's just going to be approved, and so you can work on this even if you have if you don't have like very good result at the end.
How about the case of energetics? To come back to the QEI topic, is the fact that startups, at least the large ones, I mean over 50 people, have a critical mass of engineers and researchers. Is it enabling them to conduct better R&D on the energetics in the full stack approach compared to very specialized academic groups, or teaming up with academic groups? So is it a kind of organization that favors that kind of thing? It's maybe too early to tell because we started.
I mean, at least, so I mean, it's hard to judge, but at least it's very easy to go and talk to the others within the same company, right? So we can just set up a meeting with the experimentalists that are just next door, and we talk about energetics. And it's not something that we could do easily if I was just doing theory in a theory group. So yeah, but that being so, I've said a lot of benefits for working in industry, but of course, like there is also plenty of benefits in working in academia, and I don't want to downplay those benefits. And we need people working in academia, of course. So.
Thank you. I would like to go back to the algorithm optimization. It's a query. I don't work in algorithms, so maybe it's not. Anyway, it's my query. So you mentioned that, Pierre Jagger, that he says you find it as a stumbling block, the point of getting better optimization for algorithm. And also, if I remember correctly, that there was recently a breakthrough in 40% reduction in some important algorithm. My point is, one of the issue I can see there, though, is that each of the different hardware have a different set of native gates. So even if you optimize, for example, your algorithm by 40% in a certain type of gates, then you have to transpile it, and then can multiply the number of gates by, I don't know, you put there a factor. So ideally, one would like to have an agnostic type of optimization for your algorithm, but I don't know even if this is possible. I don't work in this field. So what's your feeling there? Do you think there is, I don't know, a best set of native gates that could always allow for better optimization? Do you think an agnostic type of optimizer is possible? Or we simply go back to the fact that every company has its own transpiler that will try to optimize at the end the code?
Thanks for the question. That's exactly what we tried and will continue to try to do with Qiskit. I think it was in September we published what we call the bench press. It's a 1,000 test benchmark run on Qiskit without taking care of the hardware underlying. That means that we test the quality of Qiskit in transpilation for every kind of hardware, physical hardware, star, all-to-all, hexalattice as we have, square lattice, etc., of different kind of physical implementation hardware. And we optimize Qiskit for every of this kind of transpilation. And it is open source. and it is generic right now. I mean, that's exactly what we have. I mean, what we try to do. It's not. I mean, it's a never-ending story. Optimization. It's you can always optimize. Then you should never say that you succeed, but at least we reach a point that we were very. I mean, we were better, not very. We were better than what we have done in the past, and we continue to improve. And I think I totally agree with you. That's something that the overall, let's say, community should address on that. And Qiskit is not IBM. I think that's 75% of the commit to the Qiskit code are not done by IBM. Then that's very clear. And Apache V2 licensee, please use and resell.
Any other
it's a very specific answer. I'm sorry for that, but that's exactly the case.
Thank you.
Any other question? Ariane?
It's not a question, it's more... Yeah, no, it's not a question, more like just a little comment going back on this transition between academia and industry, because so I've experienced that myself, and it was more to leave maybe a more positive note on the fact that a lot of people from the academia might be now attracted to the industry. I want to see it also as an opportunity to rebalance the fact. I mean, I think it's amazing that now you have opportunities in the industry to do research as well. Because also I think that in France, academia has become extremely competitive, and people who now want to make it in academia have to perform, in the sense you need to publish papers, you need to teach, you need to do everything. And I think this selects people who have a mindset that is actually a bit more suited to startup environments. And this was my impression. And so the fact that now maybe you have this opportunity to go do research in the industry would leave more space in academia for the weirdos who want to do blue sky research, and maybe this is good. So yeah, just my 2 cents on this.
So you want to comment, or it's a very good feedback, yes. I have a last question for you guys. What do you think, I mean, the QEI should be or should do or should organize to improve the way this topic is being handled in the industry, in the academia sector? It's a very broad question. You all know about the shape and form of the QEI right now, so there's probably room for improvement, so suggestions.
Well, I think like this kind of events, and again, thank you, Robert, for this. It's wonderful. Like, we talk to each other. We have a line of wonderful talks. It's really on spot on the topic. So yeah, like bringing people together and having like a way to communicate on the topic. It's very nice. Yeah, I'm not sure. I think that the QEI is doing very well in like trying to propose ideas, but not imposing ideas, not imposing a research agenda. It's just trying to communicate, educate on the topic, and we saw that it became quickly like a kind of an important research project for people. And yeah, so like the communication and making the community grow, I think it's really the mission of the QEI, and at least from what I see for now, I think it's doing well in that respect.
Yeah, of course, congratulations guys for the QEI. It's very exciting, very important for us. If I do have a suggestion, having some white paper, annual white paper around energy initiative and energy benchmark or whatever would be interesting for us.
It's a good idea.
I think it's yours.
Others?
I just want. This is Ariane. This is correct. I just want to answer to that. We like the weirdos as well. This is just. I want to tell you this because I remember that I discussed that with some people from ST Microelectronics. So we have the capabilities, from some I should say weirdos, but some people that are basically like if they are like extremely talented on some subjects, and usually this is correlated somehow. I discuss, and I was with this guy from ST Microelectronics, which is basically like a very big company. He told me that basically you know how to manage these people to be efficient for the company, and we have these capabilities, and there is a management effort in all the company that is there to basically what we want is to have like to perform, right? And if we need a weirdo, we know how to do that. And this is something that I learned going to this industry, because in CNRS you don't have any management. You know, you manage yourself, and this is largely enough. But here, and this is the way that
COI is a bit different to some extent. No?
They try, but somehow this is a little bit. But you know, the structure that I saw in companies nowadays, you know, and we need these people as well, if they are well placed and to put them in position to perform. So I just want to, you know, I don't want to have all the weirdos in the blue sky research. I want to attract them and to convince them that they can do something good. You know, I always say that, you know, I went to the fact that my mother told me that, what do you do, like doing CNRS, nobody cares. And now that no, but this is true, and so she was very, very aggressive, and I was thinking that I was doing like the most fantastic job in life, but she said, you are useless, only 10 people are reading your papers. And at some point I say, okay, there is some truth in it, right? And to have some impact about like some like economical or like some kind to be integrated in the world, it might be like some good ideas, and this is not only like for like not weirdos people. And I think that anybody can come and feel free to ask and to visit our labs and to see how we work. And I think this is true for all the company here, but I say that also for Quobly. We are like very open-minded, and we have like very, very difficult challenges to tackle, and we know how to integrate anybody. We are like inclusive, so to speak. So please come and visit.
Regarding your question, Olivier, I do think that the full stack approach that the QEI is working on, I mean, ongoing, I think is definitely what we want to do from an energetic point of view. It's not the energetic of the qubit, it's not the energetic of the cryostat, it's not the energetic of the coupling, it's not the energetic of the software, it's
the whole story.
Whole story, and it's a huge optimization problem that maybe we will need a quantum computer to tackle anyway. And then coming back to the weirdo, Tristan, I definitely agree with you. There is one value in IBM, which is treasure the wild duck. When you onboard as a manager in IBM, the first step is recognize the wild duck in your team, you know, the guy that is the weirdo, and treasure it, because one of the wild duck we have was Mr. Mandelbrot, and he just invited.
And Denar, and Bennett, and Landauer.
And others. and that's the kind of people that if you think from a pure commercial standpoint, you just do not hire them. If you do research like Quobly is doing, like Qilimanjaro is doing, like Pasqal, Constantin was there, like Quandela is doing, like IBM is doing, is clearly Alice and Bob, which is in the room. That's clearly the kind of people that we want, because it will help us grow. Once again, remember, Mandelbrot was in IBM, and some people say, well, you know what, we don't care, let's fire that guy.
He died recently, no?
Yeah, he died, yeah.
Old, very old.
Exactly. That's the most useful people. Generally, you don't have to pay them that much, and they work a lot. You know, that's wonderful.
I would like to do a Mandelbrot curve with a quantum computer to see.
You want some?
There was another question over there? Yep, Robert.
There's a trade here.
I think we should close. We are...
So I have a question, but we can discuss it afterwards. So one of the questions as one of the organizers of these sorts of events is that we clearly have a large imbalance in the sense that we're nearly all physicists and very few engineers, and more or less no enabling technology people at this particular workshop, which is partly all 100% my fault, let's say. So I want to know, and I guess it's a private discussion we can have afterwards, but how the connection between engineers, particularly people developing enabling technologies, works in your companies? Are there ways to make a connection between most of you who are maybe a bit more on the physics side and the people who are more on the engineering side? Are there things we should be doing? Things like, so I guess you've already encountered those sorts of problems in your team building, so maybe we can learn from you.
Christophe?
Yes.
He's done that, so...
No. I think he wants to say about like how to attract engineers.
Yeah.
How to attract them to our community and make sure we're talking the same language, right?
But not necessarily in the same company, yeah.
So I will give you my experience about that, because in Quobly we have like, I think I usually say that, we have the less physicists inside a quantum company that I know. Right, so there are very, very few physicists, and we try to, and there is these two pillars, and we attract some people from like, we have like a huge, ecosystem of semiconductor industry, and they are like extremely valuable for us.
The guys, how to use EDAs to design circuits,
so
stuff like that.
Circuit and to do that. So. How does that work is the fact that, this is like a diversity thing, is the fact that they are usually like extremely efficient to produce results. They are like trained to like this kind of like short scale delivery and to organize everything where we are not good at all. And this is like the main problem of discussion. We are like academics, we are like a little bit like dreamers, right? We have like many ideas all the time, but we never succeed many objectives. And so the way that we deal that in Quobly is the fact that this is just like trying to speak the same language, try to attract them, to convince them that this is interesting, because this is mostly like the most difficult thing for them. To go to something which an objective which is not well defined. It's long term, and I think that this is the main, and also the fact that I have the impression somehow in Quobly that they are feeling a little bit not knowledgeable enough. So there is a training thing, and spending some time, and I spend a lot of time with them in order to basically tell them that quantum computing and quantum mechanics is not like something extremely difficult, and try to basically have like some conversation with them in order to drive them to the quantum world, which is new for most of these people. And I think this is what we do in Quobly, to try to incorporate many different people around the objectives of the company.
I think we could wrap up now. We had a very nice discussions, so we can applaud our guests. And I don't know, Robert, if we have an after right now, or we can have drinks or whatever. No, it's closed. Well, I can do that. Yeah. Thank you very much. See you tomorrow morning.